Hi everybody, in this video I'm going to go over APEX section 7.2.1 solutions, and this is part 1 of that study section. There's going to be a second video for part 2. Okay, this is talking about solutions. Solutions is when one substance dissolves in another, right? So if we have a beaker full of water and we put some salt in it, at first the salt will be all together, but then after a while it'll spread out and you'll get a nice even solution. Okay, so I want to talk about how this is happening at a molecular level. So let's look at that. Okay, so we know salt is sodium chloride. So we have a sodium ion and a chloride ion. We also have a whole bunch of water molecules. Now, we know that water is a polar molecule, and that means it has a partial positive charge and a partial negative charge. So because oxygen is more electronegative than hydrogen, the oxygen end is partially negative, and the hydrogen end is partially positive. So now we have a partial positive charge over here and a negative charge from that chlorine ion. So what happens is the hydrogen end of water actually ends up attracting to that negative chlorine ion. So it's going to surround it and be attracted to that, okay? And so that's going to start to pull that chlorine molecule away from the sodium, okay? Because the hydrogen end is partially positive, it is attracted to the negative chlorine ion, so it's going to pull it away from the sodium ion. Now, at the same time, we have water molecules over here. And again, our oxygen is partially negative because it is more electronegative, it pulls the electrons towards it, and the hydrogen end is partially positive. So now the partial negative of the oxygen end is going to be attracted to the positive from the sodium ion. So at the same time, the oxygen end is going to be attracted to the sodium and pull that apart from chlorine too. So what you end up getting after a while is your sodium and your chlorine separate. So you have your sodium ion here, and it is going to be completely surrounded by water molecules with the oxygen end being attracted to it because, again, it is partially negative. Okay. At the same time, you have your chlorine has been separated, and it is going to be completely surrounded by water molecules with the hydrogen end closer to it because it is partially positive. Okay, and so these things are going to end up separating from each other. So we call the sodium chloride here, we call it the solute. And the solute is the substance that gets dissolved. Okay, we call the water the solvent. And that's the substance that does the dissolving. Okay, and so when we have our sodium chloride, our solute dissolving in our water solvent, there are really 3 steps that are happening here. So let's go through that. The first thing is that the solute separates. Okay, the sodium and the chlorine start to separate from each other. The second thing is that the solvent, it overcomes the intermolecular forces holding it together and it separates as well. Remember that water molecules are held together by hydrogen bonds with other water molecules, so they need to separate in order to interact with the solute. And that's our third step, is our solute and our solvent interact. Okay, so we need to understand how the solution dissolves, right? We need to understand that at a molecular level. We also need to understand the difference between a solute and a solvent. So let's do one more example here. If we have sugar water, then the sugar is the thing that gets dissolved, that is our solute, and our water is the thing that does the dissolving, so that's our solvent. Okay, so we want to know the difference between a solute and a solvent. Okay, so now let's move on. Now, you might have heard of an electrolyte solution, right? So you've heard that Gatorade is full of electrolytes. What does that mean? Now, electrolyte solutions, they are a special kind of solution that conducts electricity. The reason they conduct electricity is because they have dissolved ions. And therefore, they have moving charges, and it conducts electricity. Okay? So in an electrolyte solution, the solute must be ionic. So what we just drew here, the sodium chloride in water, is an example of an electrolyte solution. We have these dissolved ions, right? Sodium and chlorine are both ions. So you have charges that move, that produces electricity. So sodium chloride in water is an example of an electrolyte solution. Let's do a couple more examples. If we have potassium iodide as our solute, potassium is a metal, iodine is a nonmetal, so we know this is an ionic substance. And all ionic substances form electrolyte solutions. So this is an electrolyte. Okay. If you have carbon dioxide as your solute, like in the case of seltzer, right? Carbon dioxide, carbon is a nonmetal, oxygen is also a nonmetal, so this is covalent substance. So it is not ionic, so it is a non-electrolyte. Okay? So when you have a sports drink like Gatorade, and it says it's full of electrolytes, what it's really full of is sodium chloride. Just add a lot of table salt to it. And since table salt is ionic, it adds electrolytes. Okay, so now you know when you see an ad that says, this is full of electrolytes, you know it's just full of salt. Okay. All right, next thing is that in order for a solute and a solvent to dissolve in each other, form a solution, they need to have the same polarity. And we've talked about this before. So let's look at water again, our example. So water, we know, is polar, right? Again, it has separation of charge. We have a partial negative on the oxygen end, partial positive on the hydrogen end, and so it is a polar molecule. Now, only other polar molecules will be able to dissolve in water. So for example, let's say we have ammonia, we have a nitrogen, ammonia is NH3, looks like this. So ammonia is not symmetric, so it has a partial negative on the top and a partial positive on the bottom with hydrogen. So this makes it a polar molecule. So that means it will dissolve in water. Okay, and water and ammonia can form a solution. However, you could have something different. You could have boron trihydride. Okay, now boron trihydride still has 3 hydrogens, but they're spread out more evenly. And as a result, you get a symmetric molecule. And symmetric molecules, we've said, are nonpolar. So that means it's nonpolar, so it does not dissolve in water. Okay, so the idea here is polar molecules will only form solutions with other polar molecules, and nonpolar molecules will only form solutions with other nonpolar molecules. Okay, so this actually allows us to explain how soap works. So soap is a molecule, looks like this, and it has one polar end. And so we know water is polar, so the polar end is going to be attracted to water. And it has one nonpolar end. And so that side is not going to be attracted to water. It's going to be attracted to non-polar substances like oil or fat. Okay. So now if you're washing your hands and your hands have a whole bunch of oil on them, the non-polar end of the soap molecule is going to be attracted to that oil, and it's going to start to surround it. Okay. Meanwhile, you still have your polar end of soap, and that is attracted to the water that is surrounding it when you're washing your hands. So what happens is the soap molecule totally surrounds that oil, and it creates what we call a mycel. Right? A mycel is that bit of oil surrounded by the soap molecules. And since the outside layer of these soap molecules is polar, it's attracted to water, so this whole thing is going to go right down your drain and wash away. Okay, so this is how soap works. You're also going to watch a video after this about how soap is so good at destroying the coronavirus, because our coronavirus is very similar to oil. So one end is going to attract to it, and it's going to sort of pull apart the virus, and the other end is going to make it all dissolve in the water. So you're going to watch a video on that in just a minute. Now, one last thing before we go, I want to talk about heterogeneous and homogeneous mixtures. Okay, so a homogeneous mixture is a mixture in which the substances are evenly mixed. Okay, so all solutions are homogeneous mixtures. Okay, because they are spread out very evenly throughout. So an example would be salt water. Right? If you have salt water, you have your water, and the salt is all evenly spread out, and if you look at it, it just looks all even throughout. So that's a homogeneous mixture. The opposite of that is a heterogeneous mixture. So this is a mixture that is not the same throughout. Okay, so for example, if you have a bowl of cereal with milk in it, okay, so you're going to have your bowl, and it's going to have some cereal in it, okay, and then it's going to have some milk around it, right? So clearly there are chunks of something different spread out in this. So this is a heterogeneous mixture, a mixture that's not the same throughout. It's not even throughout. You can tell your Cheerios are sticking out from your milk, okay? So we want to know the difference between a homogeneous and a heterogeneous mixture. All right, so from this first part of solutions, we need to know the difference between a solute and a solvent. We need to understand what's happening at a molecular level when a solute dissolves in a solvent, right? Like the water molecules are surrounding the different ions and pulling them apart because they are attracted. We need to understand what an electrolyte is, right? That an electrolyte is just an ionic solute in a solution, and that makes it conduct electricity. We need to know that polar substances dissolve in other polar substances and non-polar substances dissolve in non-polar substances. So you need to have the same polarity to form a solution. We need to be able to use that to explain how soap works, and we need to know the difference between a homogeneous and heterogeneous mixture. Okay, now after you've watched this, you're going to watch the Vox video on how soap destroys the coronavirus, and then stay tuned for part 2, which we're going to do in a couple more days. Thank you.